In the first bitter weeks of 1942, Boeing's Plant 2 in Seattle was supposed to be a thunderstorm, an industrial avalanche of B-17 flying fortresses that would one day darken the skies over Nazi Germany. Instead, the massive assembly hall stood frozen in a suffocating stillness. 63 skeletal bombers, nothing but aluminum ribs and unfinished wings, sat motionless under the factory lights, each one a monument to a promise America was failing to keep. The Army Air Forces had ordered 3,615 bombers for that year. By mid-January, Boeing had delivered 9, a single digit. General Henry Hap Arnold was not disappointed. He was incandescent. Behind closed doors, on January 15th, his fury seared through Boeing's executives like acid. Without a fleet of heavy bombers, there could be no strategic air campaign. Without that campaign, the ground war in Europe would devour American lives for years. Every day Boeing failed to deliver was another day the Third Reich gained ground. The math was merciless. And yet, the problem wasn't manpower. Boeing had hired 30,000 workers in 6 months, many of them women stepping onto a factory floor for the first time. It wasn't materials. Mountains of aluminum from Alcoa sat waiting to be shaped. The crisis was inside the machine itself. The B-17 was too complex for the world that needed it. Each bomber was a 140,000-piece puzzle. Each wing demanded more than 12,000 rivets. The established methods of aircraft construction, methods perfectly suited for smaller, simpler planes, collapsed against this new reality. Every morning at 5, Philip Johnson, Boeing's head of production, walked the line like a man pacing through a slow-motion catastrophe. At Wing Assembly Station number 4, 17 workers were packed shoulder to shoulder, stumbling over hoses, fighting for the same square foot of space. Riveters, buckers, inspectors, each one waiting for the other to move. A choreography of frustration, a ballet of wasted time. Johnson had timed it himself, more than 20 hours to finish a single wing. Meanwhile, over Europe, the Royal Air Force was losing bombers faster than Boeing could build them. Every hour lost in Seattle meant another blackened crater in England, another Allied ship sunk in the Atlantic, another German factory untouched in the Ruhr. The paralysis wasn't just costing time, it was costing lives. Engineers tried everything: new access ports, custom jigs, smaller crews, bigger crews. Nothing worked. The bottleneck was baked into the wing's DNA. The sacred blueprints demanded each rivet line be installed in perfect parallel rows. Clean, predictable, theoretical. But theory didn't account for human bodies tripping over each other, or for heat from 17 workers expanding the metal just enough to misalign thousands of holes. The engineering was flawless. The reality was chaos. Quality inspectors hated the wings. Every 10th rivet had to be checked with a borescope. If they found a flawed rivet, it meant drilling it out, a 3-minute penalty. Across 12,000 rivets, those minutes became wars. No manual mentioned what happened when the metal distorted because 17 people breathed on it for 20 consecutive hours. But that was the world they lived in. And in that world worked a man named Frank Shamansky. He didn't look like someone destined to alter the trajectory of a global war. 5'7", 31 years old. Hands stained black from aluminum dust. Before Pearl Harbor, he'd fitted car doors at Chrysler in Detroit. The kind of repetitive work where your mind wanders, but your hands move like they've known the rhythm forever. Frank joined Boeing's swing shift, working from 4 in the afternoon to midnight. And what separated him from the others wasn't speed. It was his gaze. Frank saw the whole system. He saw Jenkins stuck on row 3 because Patterson on row 2 was trapped behind quality control. He saw riveters losing minutes reconnecting hoses. He saw how human exhaustion was quietly sabotaging American air power. On February 4th, while eating his sandwich on a crate, Frank stared at a finished wing being hoisted into place. The rivet rows were beautiful, mathematical, elegant. But his mind drifted back to Chrysler. Door panels weren't attached in straight lines. They were attached from multiple points at once, converging inward. It allowed workers to move in parallel, never crossing paths. He looked at the wing diagram pinned to the bulletin board. Then he noticed something no one else had seen. The wing wasn't a flat panel. It had ribs, hollows, access hatches, natural entry points, places where workers could operate without interfering with one another. That night, using the back of his time card, Frank began sketching something that looked heretical. Clusters of rivets around internal ribs, like constellations, with lines radiating outward instead of marching in rows. A pattern that would allow 5 workers to rivet simultaneously without ever touching the same space. A pattern based not on theory, but on the geography of the wing itself. The next week, he showed the sketch to his supervisor, Bill Hendricks. Hendricks stared at it for a long, hard minute. "This violates every principle of structural loading," he said. "This goes against everything in the textbooks." He explained von Karman's theory, stress distribution, load trajectories, how the wing flexed in flight, how the rivet rows were positioned to counter invisible forces. On paper, Frank's pattern was madness. A wing built that way could shatter midair. Men could die. But Hendricks wasn't finished. "What if the perfect design still fails?" he asked quietly, "because we build it so slowly and so poorly that it never meets its theoretical strength? What if your pattern, though imperfect on paper, creates better rivets simply because the workers aren't exhausted?" It was the first time someone saw what Frank had seen. Hendricks took the time card and went to a desperate man, Donald Douglas, assistant production manager. Douglas was weeks from being fired. Boeing was dangerously close to losing the B-17 contract to Consolidated's B-24. If Boeing didn't deliver a miracle by mid-March, the heart of the bomber program would be ripped from Seattle. So Douglas did the unthinkable. He authorized a secret experiment. On the graveyard shift, starting at midnight on February 21st, they smuggled in a scrapped wing section, damaged beyond use. Perfect for a test that could end careers. Frank refined his pattern, color-coding zones, red, blue, yellow, green, white. 5 workers. 5 territories that never overlapped. The test started at 12:14 a.m. If the old method dictated order, this new one looked like chaos. Workers above, below, inside, outside. A storm of rivet guns hammering the wing from all angles. No waiting, no tangling hoses. No heat bubble of human bodies melting the metal. After 2 hours, the wing was nearly finished. Douglas's hands shook as he checked his stopwatch. At 2:21 a.m., just 127 minutes after they began, the final rivet locked into place. Quality inspection was brutal. They expected catastrophe. Instead, they found 11 defects. The average wing had 140. But the wing still needed to survive the violence of combat. So Douglas broke protocol again. At 3:30 a.m., he ordered the structural test facility to prepare for an emergency load test. He lied, told them it was routine. At 4:15, they mounted the wing onto the hydraulic press. The machine roared to life. Gauges climbed. 1G, 3G, 6.2G, the Army requirement. The wing held. Douglas swallowed. Keep going. 7Gs, 8Gs, 8.4. It still held. They stopped the test, not because the wing was failing, but because the machine was. The wing returned to its neutral position without a single bend. No one expected this. Not the engineers, not the supervisors, not the man who drew the pattern. By accident, or perhaps by genius, Frank's clustered rivet pattern aligned perfectly with the wing's internal ribs, channeling stress through its strongest bones. It was stronger than the engineer-approved design. Stronger and 16 times faster to build. At 6 that morning, Douglas went straight to the home of James Murray, Boeing's vice president of operations. Murray arrived at the plant, saw the data, and understood instantly. This was the miracle they needed. Over the screams of the engineering department, he ordered the method into full production, effective immediately. Frank Shamansky received a new title and a $40 a week raise. It wasn't much, but history would remember what happened next. In March, Boeing delivered 47 B-17s. In April, 91. June, 186. July, 284. September, 362 bombers, more than the entire previous year. The air war shifted. The 8th Air Force could now send 100 bomber raids, then 300, then 500. Interlocking defensive fire tore apart the Luftwaffe. The raids that destroyed German ball-bearing production, the turning point of the air war, required 376 B-17s. Without Frank's pattern, those planes would never have existed. After the war, Frank's name faded. His specialist role was eliminated. He returned to Detroit, worked at Ford, died in 1971, likely unaware that his pencil sketch on a time card had helped change the shape of the world. But the legacy endured. When Boeing designed the B-47, they began not with theory, but by consulting the workers on the line. When they designed the 707, supervisors sat beside engineers from day one. Today, the principle is universal. They call it design for manufacturability. Students learn the case study, they learn the innovation, but not the name. They don't learn about Frank. Yet the lesson he left behind is universal, eternal, and quietly revolutionary. The person doing the work often understands it more profoundly than the person designing it. Smart organizations listen. Others keep building wings in 20 hours and wonder why the war is being lost.